Hello, everyone. My name is Chris Hayes, and I am a postdoc at the NRC Hertzberg Astronomy and Astrophysics Research Center. I'm very glad to be here to talk to you all today about the Gemini high-resolution optical spectrograph, GHOST, our commissioning run, and some of the first data that we've gotten for it. So starting off, GHOST is the next generation fiber-fed high-resolution optical spectrograph for Gemini South. And it's been a long time coming. The original call for proposals that GHOST turned into was back in 2011, and over the next 10 years, it was developed, built, and shipped down to Chile in spring of 2020, where it had to unfortunately sit for 2 years, as you heard, due to COVID restrictions. But fortunately, over the past few months, we've had a great team come down to Chile to assemble it and verify it, and then let us do our commissioning run. So GHOST is a project that is led by the Australian Astronomical Observatory, but effectively it's a partnership between AAO, who developed the Cassegrain unit for GHOST, the fibers and the electronics, the Australian National University, who developed the software and data pipeline, and then NRC Hertzberg, who developed the spectrometer. And of course, a team is nothing without its members. So I'd just like to show some of the faces of the people who put in all of this hard work over the past few months to put GHOST together. And of course, thanks goes out to many others, both past and present on the GHOST team. So now there is a GHOST down at Gemini South. So here you can see this giant black box is the outer enclosure of GHOST. Sitting down there in the Pier Lab underneath Gemini South. And not only does it look really nice, but it also produces really nice looking spectra. So here you can see the blue camera and the red camera from GHOST taking images, taking spectra of a chemically peculiar star. And this was all released as the first light images from Noir Lab last week. And in the bottom here, you can see a nice flat fielded spectrum of this star from this commissioning run data. So I'll talk a little bit more about the star later, but to give you a little bit of brief on the GHOST commissioning run itself. So it was originally scheduled for 9 nights at the end of June, so only about a month ago. And unfortunately, the weather looked a lot like the background here. So we had a lot of clouds at the beginning of the run, and not only clouds, and something you can't see here is very high winds. So this is a little snapshot we took of a gust of wind at 40 meters a second. This is about 140 kilometers an hour. So we had nice windy, cloudy weather for the first part of the run. And by the 8th night, we had only opened the telescope up twice, but neither were very good conditions. You could really only see the brightest stars in the sky. Gemini graciously extended our commissioning run by 3 nights so that we could finish up all of the tasks that we needed to do. Which, as it turned out, after several nights of poor weather, we got 3 excellent nights that were enough to cover all that we needed with the commissioning run tests and give us some of the data that I'll share with you today. So before I jump into the data itself, I thought I'd give you a little bit of a walkthrough of how GHOST works and some of the unique features of GHOST. So starting at the telescope, we have the Slit unit for GHOST, which you can see here. There are 2 positioners for GHOST here and here, and on each of these are small 1.2 arc-second diameter IFUs that map from here on the at the positioners into 2 pseudo slits of fibers at the spectrograph. So the first slit here with these wider fibers maps into 2 object IFUs, and this gives us our standard resolution mode of about 50,000. So you can do up to 2 objects in this 50,000 standard resolution mode. The other slit that has these more narrow fibers goes to a single high resolution 75,000 resolution object IFU and an accompanying sky IFU, whereas the sky IFU for the standard resolution sits in between the 2 objects in the pseudo slit. Along with an object and the sky, you also have a thorium xenon internal calibration lamp that's fed by a single fiber into the spectrograph so that you can do simultaneous wavelength calibration and for precision radial velocities. So once the spectrograph once the light goes down to the spectrograph, we have the next relatively unique component of Ghost, which is a slit viewer camera. So I've got an image of this slit viewer camera from the slit viewer camera down here in the bottom left. And the slit viewer camera takes a picture of these pseudo slits. So here you can see all of the fibers illuminated, and there's actually a red and a blue copy on the slit viewer camera for the light that goes into the red and the blue science cameras. And this is useful for a number of different reasons, more than I can get into in this talk, but particularly for the data reduction, for precision radio velocities, and for extracting your spectra more precisely to build up a better signal to noise. And the reason for this is that for Ghost, in very poor seeing, the fibers will all be nearly uniformly illuminated, like you can see in this image here. But in cases of good seeing, because of the way that the fibers are organized, the light will be more centrally concentrated in your pseudo slit. And so if you look at the equivalent science camera image of something like this, you can see three orders here of an object that's being observed in high resolution mode. So this is data that we took during our commissioning run. And you can see that the light is more concentrated towards the center of the order. And so by weighting these fibers higher during the data reduction, you can more optimally extract your spectra and get a better signal to noise by using the slit profile that you get from the viewer. You can also see here an illuminated thorium xenon lamp fiber, which shows up in emission lines here above the spectrum. And the slit viewer camera is also helpful because you have different observing modes of Ghost, and you want to reduce them all with the same data reduction pipeline. So for instance, you can also observe with Ghost in this dual target mode. So here you have two objects that are being observed, one that's fainter on top and one that's brighter down here on bottom. And again, you're seeing three of these orders. And then you've got the sky fibers in between, which you can see here are actually illuminated. You've got an entire skyline that stretches across all three of these IFUs. And so having a precise slit profile from your slit viewer camera helps you with figuring out where these fibers and this slit gets spread out across your spectrograph. So these are two of the observing modes of Ghost: high resolution with the thorium xenon for precision radio velocities, and then two objects in your standard resolution mode. When you combine the two resolution settings of 50,000 and 75,000 with different on-chip binning modes, you can actually get a number of different operating modes depending on your science of choice. So for instance, you can increase the spatial binning if you don't need to keep that thorium xenon fiber separate from the rest of your object. You can increase the spatial binning so that you can get a better signal to noise by reducing read noise. And you can bin in the spectral direction for the standard resolution because it's actually already oversampled, and that doesn't really lose you too much in terms of resolution. You can also push the binning a little bit further in the spatial direction. This is an example of a pair of stars that are observed with a factor of 4 binning in the spatial direction. You can see that they start to get close together when you highly bin in the spatial direction, but so you can push the binning further, but you wouldn't really want to do so with two objects. And we're exploring an option for observing with a more highly binned spectral binning that would give you a reduced resolution, but might be interesting for some science cases. In terms of sensitivity, here I have the sensitivity requirements of Ghost, which are defined. These are the AB magnitude limits that you need to reach signal to noise of 30 in 1 hour of observation. So it's something like 15 at the bluer end of Ghost's coverage, and more like 17.5 in terms of the where Ghost throughput is highest. Now, to give you a little bit of a comparison, so the red line here shows the requirements of Ghost as compared to Grace's high-res and UVES, other high-resolution spectrographs. And in the dashed black line, I'm showing what was budgeted for Ghost originally. And in the dashed red line, you see the predictions from the in-lab measurements of Ghost when it was put together in the lab. And so the fact that this is so much higher than the requirements suggests that we'll easily exceed these requirements here and provide even higher sensitivity. And currently we're working on those on-sky measurements that we took during the commissioning run, but that's a little bit more involved. So we will get back to you with more information on that in the future. So to show you a little bit of data from GHOST, I would like to show just a little bit of a gallery of objects that were observed during the commissioning run. So starting with this spectrophotometric standard star. So it's a relatively boring star, but it provides us a good set of images to show what you get from GHOST. So here you can see that you get a slit viewer camera image. You actually get many images with every observation. You also get a blue science camera image, which you can see all of the individual orders going from red to blue. And you get a red science camera image with all of the spectral orders going from red to blue on this chip. And when you just do a raw extraction, this is what you'll get. So you can see all of the arcs. Each color is a separate order, and the arcs are from the blaze of the orders, but you can see the overall throughput combined with the spectrum of this star. And you can see here the red orders and the blue orders. And you can see that there's a little dip in between because of the dichroic that splits the light between the two cameras. So looking at some fun objects, so here's the Stingray Nebula. So you've probably seen this image of the Stingray Nebula from HST. And on the right, I have a portion of the spectrum that we took from GHOST, showing the Balmer series in emission, starting with Balmer Zeta, which has this nice horned profile. And I'm just going to let this play, and you'll be able to watch as a whole bunch of Balmer lines go by, each getting lower and lower in intensity and closer together, as the Balmer lines should. Because this is a planetary nebula, it has all of these lines in emission. So you can get all the way out to Balmer 25, which is kind of fun. If you're interested in extragalactic astronomy, here's an example of a redshift 3, something like a 17th magnitude quasar that was observed with GHOST during our commissioning run. And you hardly need me to point out that in this blue camera image, you can see all of these absorption features that are from the Lyman alpha forest. And so bear with me, this is still a work in progress, of course, because we've only had this data for a few weeks now. But you can see here all of the raw orders that are extracted, and you can see all of these absorption features, which I promise are not noise, because you can zoom in and look at all of these deep absorption features from the Lyman alpha forest. So going on to the last one here, and this is my favorite because I do stellar astronomy. And this is HD 222925. This is the star that was shown off as the press release, the first light press release from NORA Lab last week. And this star is an R process enhanced star. So that means that it's enhanced in R process elements. These are heavy metal elements that are produced through high energy environments like supernovae and neutron star mergers. And this star, which is otherwise a metal poor star, has a whole bunch of these elements in it. So it's a metal poor red giant. And just to focus on some of the normal aspects of metal poor red giants, you can see here on this red camera image, you can see these two absorption lines that are the H alpha lines. It shows up in two orders. If you go redward on the camera, you can see the calcium triplet here in absorption. And if you go to the blue camera, the most obvious thing are these broad, deep absorption lines that are the calcium H and K lines and actually show up on two orders again. But you zoom in on the extracted spectrum, and you can see all of these absorption features that are showing up. And this is because at blue wavelengths, you have a whole bunch of absorption from heavy metal lines. And just to zoom in on some interesting ones for this star, this highlights a region around this europium line that is extremely deep, and you can compare it to iron, which is a more normal element, of course. And you can see these really strong europium and other R process enhanced elements like yttrium, zirconium, gadolinium, dysprosium, samarium. Some of these you might not have even heard of. And to give you a little bit of a comparison, this is from Roeder et al. 2018 that compares this exact same star in black to a star that is not enhanced in R process elements in gray. And you can see just how much stronger these lines are in the star. And so this is one of the interesting things that we would like to do with the groups here that I work with, is to push this to fainter and fainter stars to do really interesting things. And just to leave you with one last note about the spectrum. So this is the full 1D spectrum, just as a reminder that GHOST provides simultaneous coverage of the entire optical wavelength range at high resolution, going all the way from about 3,500 out to about 10,500, so about 7,000 angstroms worth of coverage. And with that, I will just summarize in saying that a lot of thanks goes out to the staff at Gemini for making the integration, verification, and commissioning so successful and safe during COVID. Hopefully you will stay tuned for more news about GHOST in the future and when it will be made available to the Gemini community. Thank you very much.
Great. Thanks so much, Chris, for that fantastic talk. It's absolutely amazing how blue GHOST is going. Are there any questions? And I'm actually going to go virtual for the first time instead of going to the room first.
No questions.
No questions virtually? Then let's go to the room.
I'll take it. A wonderful talk. Thank you. Looking at the GHOST website, there's a mention of using it to do RV follow-up of test planets as one of your science cases, and a statement that the expected RV precision is something like 10 meters per second. Given your resolution and the high resolution mode and the wavelength coverage, I would have expected that number to be a little better. And I'm wondering if you can comment on what is setting that limiting factor, if it's the lack of pressure stability or the, I don't know, blue throughput, something like that.
So I think in part it might be a little bit blue throughput. I am not, unfortunately, an expert on the precision radial velocity work, so I don't think I can comment too much on that. I can mention that the GHOST instrument is very temperature stable, but as far as getting down to those extreme precisions, I unfortunately don't have much more information.
No worries, I'll go do some more digging online. Thank you.
I can put you in touch if you want with people who might be able to answer your questions, though, if you're interested.
Oh yeah, I will find you on the Slack and ask that question.
Great.
Thanks.
Thank you.
Great. Any other questions from the room? Anything online?
There's a comment saying no questions, but great to see the beautiful GHOST data.
Oh, I think we can
Thank you.
all
Much
absolutely
appreciated.
agree with that. Great. Thanks so much, Chris, for that fantastic talk. Let's thank Chris again. And
Thank you for the opportunity.
What's the question?
We have time if you want to ask it quick.
Sorry, but actually I have a selfish question. So if the GHOST is available, so is there any specific software tool for the data reduction of the GHOST data?
So, right, yeah, GHOST is not currently yet available, and there will be data reduction software that is currently in the works. Since the first data was only taken a few weeks ago, we're starting to put the data reduction pipeline through its paces and get some of that ready to go. So hopefully that will be ready once GHOST is available to the community.
Yeah, very nice. Thank you.
Thank you.